discrete random variables. So when we look at this, there's two different types of random variables. Random variable is just the thing we are measuring, the different outcomes. Discrete means it's countable. We can count how many times it occurs. Continuous has infinite values. So for example, if the variable I was looking at was how long it takes you to write down the definitions, would that be discrete or continuous? Continuous. Can I list every possibility for how long it took you to write it down? No. And is there a specified maximum there? It can keep going forever. Okay, if I said I'm going to flip a coin and count the number of heads, is that discrete or continuous? Discrete. Okay, it is countable. If I said I am going to flip a coin until I get 100 heads, okay, that's still discrete. We can count the heads, but would that one have a maximum value? No. So discrete doesn't mean that you have necessarily a certain stopping point, but it means that your outcomes, you can count all the possible outcomes there. All right, so if I am trying to decide if the following are discrete or continuous. The number of light bulbs that burn out in a room of 10 light bulbs in the next year. Is that discrete or continuous? Discrete. If I ask you for the possible values, what's the smallest x could be? Yeah, it's possible that none of my light bulbs burn out, or 1, or 2. Does it just keep going forever? No, what's the most? 10. So that one does have a stopping point. The number of leaves on a randomly selected oak tree. Discrete or continuous? Can we count them if we want to? We can. Probably don't want to, but we can. So it is technically discrete. What's the smallest it could be? 0. 1, 2. Is there a maximum on this one? No, so that one could keep going. The length of time between calls to 911. That would be continuous. Okay, if I ask for the possible values, can you have negatives? No. Can we have a true 0? No, because even if we're talking about fraction of a second, there is some kind of difference. So it would just be anything greater than 0. But I can't just say 1, 2, 3, 4 because we could have decimals or fractions in there. Do you guys understand the difference between discrete and continuous? Okay. So today our focus is on the discrete. And we are going to be making probability distributions for those discrete variables. So we've done probability distributions before. What is a probability distribution? A chart. And it has all of our x's and we call them P of x, the probabilities. So if I said, suppose a basketball player is asked to shoot 3 free throws. Create a possible probability distribution for x equals 0, 1, 2, or 3 shots made. So, do you guys agree that 0 through 3 are the only possible values here? You're going to shoot 3 times. And I didn't tell you any information about what percentage this player usually makes. So I can't really calculate actual probabilities here.
17, 11.
You're welcome. But we can make up some because I said a possible. So give me a possible probability for 0. 0.14. All right, what about 1? Okay. What about 2? All right. Do I get to choose whatever I want for 3 then? No, because what do we know about these probability distributions? They have to add up to 1. Every single probability has to be some number between 0 and 1, and the sum has to be 1. So if those were the probabilities for 0, 1, or 2, what do you get for your probability of 3? No, 55, because those add up to 45. Okay. So that is a possible probability distribution. I'm going to put a couple up here. I want you guys to look at each of them and decide if it be a probability distribution or not. If it is not, tell me why. So take a second. Is the second one. Why? And another, it has a couple problems. If it didn't add 1, and we also have a negative, and you can't have that. It's the last one. Yes, every probability is between 0 and 1. Altogether, they add up to 1. All right. So, we might be asked to describe the shape of a distribution. Remember, we've done this before. Skewed left, skewed right, or symmetric, bell-shaped. To do that, we probably need some kind of graph. So you can graph a probability distribution. You can do it different ways. You could do like a histogram on your calculator. This one isn't too hard. We could do even just like a line graph here. What's going to be on my y-axis? It looks like we have everything up to okay, and then my x-axis is our possible values, or in this case it was the number of movies. So we have our 0. So 0 had a probability of 0.06. 1 was 0.58. And I didn't specify what kind of graph, so you could do different types. We just need something to look at here. So what would you say about this shape? If we think about it, it peaks right here, and then we have a lot of points trailing off to the right, so it is skewed right. The shape of our data is going to be a lot more important as we get into chapter 7, 8, and 9. We are really going to require our data to be nice, symmetric, for all of that stuff to work. So being able to look at your data and decide if it's skewed is very important. All right, any questions so far? Next thing, we have a formula. So the mean for a discrete random variable. And this is, just like everything else, on your formula sheet. We are now in chapter 6, and it tells you right there, the mu is the sum of your x times p of x. So we've made a probability distribution. To get the mean for that, we have to take each value times its probability and add those up. Okay, the reason it works is X is essentially the number of times it comes out. So if, you know, making 2 free throws, that happens twice. So you take the probability times 2 there. This is the mean. It's also sometimes called the expected value. So expected value is what value we would expect if we repeated our experiment many, many times. We know that in general, if I flip a coin 10 times, I'm probably not going to get 5 heads and 5 tails. Okay, but if I flip it 500 times, it starts to look closer to a 50-50. So as we have more and more trials, we should see values approaching this mean or the expected value. So we're going to try finding a couple of those. So this table shows us the mean number of DVDs that were rented from a Redbox on a single visit. So we have our X and our P of X. If I want to find the mean, what am I going to have to do? Multiply and add them all up. The mean you just wrote down is the sum of all the X times P of X's. So we just take our X times the probability of that happening. So 0 times 0.06, 0. 1 times 0.58, 0.58. 2 times 0.22, 0.44. 3 times 0.1, 0.3. 4 times 0.03. 0.12, 5 times 0.01. And then what do? Add them up. What'd you get? 0.149 or 1.49? So that is our mean. Now, is it possible for somebody to walk up there and rent 1.49 movies? No. But it's saying if I sat and I watched that for a full week, and I recorded every time someone came and the number they rented, and then I found the average of those, add them all up, divide by the number of customers, it should be close to 1.49. Does that make sense to everyone? I think I'm actually going to skip one example. I'm going to go to this. So suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. The probability the female will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. expected value is the same thing as what? The mean of those discrete variables. And mean is just the sum of x times p of x. So if I'm asking you to find the expected value, we have to get the mean. We need a probability distribution. Okay, so let's think about the two scenarios here. They sell a life insurance policy. Do they have to pay that person $250,000? Okay, when do they actually end up paying that money? If the person passes away, then they have to pay the money. Okay, so if they don't, if that person lives for the year, then how much money does the company make? $530. That's what the person paid them, right? So the value, the X, the company could make $530. And that happens if the person lives a whole year. And what's the probability the person lives the whole year? Okay, but the alternative. If the person doesn't live, what's the probability that the person does not live? And how did you get that? 1 minus. Those are the only two possible outcomes. Either they live or they don't. Okay. If they don't, what happens? The company has to pay $250,000. Now, technically, they didn't lose all $250,000 because at the beginning of the year they collected $530. So to figure out how much they lose, what do you need to do? Subtract. And how would I show that that is money they are losing? Because we're finding the value to the insurance company. So the insurance company would lose. So now if I want my mean, we have to multiply those. And then we add them together. And we get an expected value for mean of what? So this is the kind of thing that actuaries do. And they work for insurance companies and they will look, okay, if you have these risk factors and you're in this age group, here is the probability that you would survive. So how much should we charge for your premiums to guarantee that we're not losing money at the end? Now, is this really a true guarantee? No. If they only insure 100 people, is this going to work? No. But if they insure enough people, then in theory, unless, we know that probabilities don't always happen, this is what's expected, but something could change that. In theory, if they insure enough people, then they would expect to turn a profit. So they have to decide how much do we have to charge to make sure that we're not going to lose money in this. Questions on that? Last thing we can do, standard deviations for a discrete. Doesn't this look kind of familiar? The sum of x squared or x minus the mean squared times p of x. Does that sound familiar? You look at your formula sheet back in chapter 3 when we were talking about standard deviations. We had something very similar. We had our value minus the mean squared, but we divided by our number of items. Here, we're not dividing by the number because we're multiplying by the probability, and the probability has already taken into account the number of items. And I tell you, find standard deviation and variance. All right, so typically, if we had the original data, we would probably just put this in our calculator and do that. And you actually still can use your calculator. I'm going to show you how in a second. But if we want to do this by hand, we need to use our formula. We have to find, I'm going to add another row to this table. So I'm going to cheat for a second because I don't have enough room right now. Okay, so we're going to add one more column, x squared p of x. And really, you can either go through and 0 squared times your probability, or if you already have x p of x, all you really have to do to get an x squared is take this times your x again. So 0 times 0 is still 0. 0.58 times 1 again is 0.58. 0.44 times 2. 0.3 times 3. 0.12 times 4. 0.05 times 5. And so if we are doing that second formula, standard deviation is the square root of the sum of the x squared p of x's minus the mean squared. So if we add all these up, square root, does that up to 3.09 minus, what did we have for our mean? Square root 3.09 minus 1.49 squared. And that gives me a standard deviation of 0.9327. We haven't done variance in a while, but how do you find variance? So we get 0.8699 for the variance. Any questions? If you want to do this on your calculator, you're going to go back and you're going to put your x's in L1 and your p of x's in L2. So now go to stat, calculate one variable statistics. Your list should say L1, but then right now under that it says frequency list. That's like the weight, that's our probability. So you need to set under frequency list, that should be L2. So if you do second, the number 2, that sets that to L2. And then if you go to calculate, your mean is 1.49. We don't have a sample standard deviation, but our population standard deviation was 0.96 or 0.9327, just like we got. Did everybody get it to work? So when we have those probabilities, that is your frequency when you do your one variables. Your list is L1 and for this frequency is L2. Everybody get it? Alright. So here is the assignment, just like we've been doing. If the question says find and interpret the probability, you don't have to do the interpret. If the only thing the question says is interpret, then you do.